Okay, here we go. All right, so like I just said, I have a review for you for the final exam. So that way you'll have the weekend to kind of go over that. And also I can answer questions that you have on it on Monday, and then our final's on Wednesday, right? So I'll give that to you today. I also updated the grades, and there were some issues on those polynomial functions. The ones, you know, I actually went through and graded them. So I think maybe Monday we can go over that. If you have questions over it, I can answer those. I just, you know, I'll hand them back today, and then you can kind of go home and see if you can figure out what went wrong. Let me just go ahead and pass those around. Does anyone have any objections to me passing these around, just letting everyone pick theirs out? The grades are on them, so that's why I'm asking. Is everyone okay with that? Any objections? Okay, so just go through these, pick yours out, and then pass the pile around. Okay, so what are we doing today? How are those rational functions? Is that something we probably need to talk about again on Monday? Yeah. Okay. So I'm going to try and let Monday be a review day, but I'm really thinking it's going to be the second half of the class on Monday will be review. The first half, we're going to be finishing up what we're going to start today. All right? So we have now moved on. We've done linear functions, right? We've done linear, we've done quadratic, we've done polynomials, we've done rational. Okay? We also remember that linear, quadratic, and polynomial all fall into the same category. Like linear and quadratic are both polynomials. Rational functions looked very different, right, than polynomials. And now we have two more to cover. We have exponential, and we have logarithmic. Those are the two other functions we're going to cover. We're going to try and cover these today. And there's some good news here, all right? Exponential functions and logarithmic functions, I believe, are the easiest, well, other than lines. Lines are pretty easy, but sometimes lines can be problematic. I think exponential and logs are the easiest to graph. The problem with the exponential and log is that I think they're the most difficult to understand. And a lot of it has to do with the notation. So I'm going to start this whole idea off here of exponential functions with an example. And the idea here is that, like we've talked about, linear functions were good at representing a certain type of growth of a function. You know, we talked about like hourly rates, or you know, you make $8 an hour, whatever it is. Linear functions are good at modeling that. Quadratics were the parabolas. We talked about that. Polynomials like stock market. Rational functions, I talked about last class, were, you know, things that are kind of decaying over time, like probabilities. And now these two. So exponential, here's my first example. How do I want to, yeah, I'll do it this way. Okay, so I have a sheet of paper here, all right? This is a rectangle. Everybody see one rectangle? Right? One rectangle here, okay? So I'm going to make a t-table, kind of like our x and our y. But here I'm going to put the number of folds that I have in the paper, and then here is going to be the number of folds. This is going to be the number of rectangles that you see, okay? So if I don't fold the paper, everyone sees one rectangle, right? No folds, one rectangle. Now if I fold it, I'm going to create this crease, right here. And when I open it back up, how many rectangles do you see if we're including the crease as like a boundary here? Two rectangles, right? You got this one and this one, right? So if I fold it one time, I'm going to have two. Now, what if I fold it that one time again and now fold it again? When I open this up, how many am I going to have? I'm going to have four, right? Everyone see the four? Okay. So two folds gave me four. Any predictions if I do this a third time? 6? 8? Let's see. So how many do you see? See 8, 4 across the top, 2 down the side. So 4 times 2 is 8. So with 3 folds, I got 8. How about for 4 folds? What do you think? 16. So we open this up. Now I have 4 across the top, 4 down the side. 4 times 4 is 16, right? Do y'all see a pattern here? What's happening every time I fold it? I'm doubling it, right? Doubling this. So I started out with 1, I folded it. That means I multiplied it by 2 and became 2. 2 times 2 again is 4. 4 times 2 again is 8. 8 times 2 again is 16. So if we were able to do 5 folds, we get 32 rectangles. And this would continue, right? So now let me ask you this question. If I could fold it 20 times, I got to continue my table over here, right? Folds, rectangles. If I were able to fold it 20 times, how many rectangles would I have? This is a difficult question. So one thing you could do is you could just complete the table, couldn't you? You go 7, 8, 9, 10, 11, 12, and just until you get to 20, couldn't you? But that would take a little bit of time. The question is, does this relationship that we have between these numbers, is there a function? Is there a function that if we put this in as the input, x, this is the output, y, right? So this is input, this is output. Is there a function that will do this for us? So all I have to do is plug 20 into the function and it spits out the answer. Well, maybe. Okay, that's the whole idea here. Can we come up with a function? And if we try and do it with a linear function or a quadratic or a polynomial or a rational, it won't work. There is no rational function that behaves this way. There's no polynomial function that behaves this way. There's no quadratic function that behaves this way. I mean, you could try something like this. Maybe you think it's x squared. I don't know. I'm just throwing something out there. Maybe you think it's x squared. Is this function doing this? So if I plug in 0, does it spit out 1? No, right? 0 squared is not 1. If I plug in 1, does it spit out 2? Well, 1 squared is 1, right? If I plug in 2, does it spit out 4? 2 squared? Yeah, it does. It works for just this one, though, right? It doesn't work for all of them. The question is there a function that would work for all of these? Understand the question? Okay, so in order to help you see that there is a function, I'm gonna do something over here and see if you agree with me or not. Do you agree that I could rewrite 2 as 2 to the first power? Yes? And I could rewrite 4 as 2 squared. And 8 is 2 times 2 times 2. That's 2 cubed, isn't it? And 16 would be 2 times that, which would be 2 to the 4th. And then we'd have 2 to the 5th, right? And do you see something that these all have in common? They all have the same number on the bottom, right? We call that the base. The base is 2 for all of these, right? And then what about the exponents? The exponent 1 is actually the input, isn't it? This 2 is that number. This 3 is that number. This 4 is that number. This 5 is that number, right? Now, does it work for the first one? I skipped this one on purpose. This would have to be 2 to what power in order for it to follow this pattern?
0.
2 to the 0. Is 2 to the 0 1? Yes. Any number raised to the 0 is 1. All right? So in general, x to the 0 is 1. This works all the time so long as x isn't 0. Right? If you have 0 to the 0, that's something else. We don't deal with that in this class. So as long as this number down here is not 0, then if we raise it to the 0, we get 1. So this works, doesn't it? So to answer this question, I really just need to figure out what do I need to figure out? I'd maybe need a calculator for this. 2 raised to the 20th power, right? That's what I'd have to do. That means 2 times 2 times 2, 20 times. So this is where we need to get our calculators out. And we're going to need our calculators today, all day. Uh-oh. Where's my calculator? There it is. All right, so on your calculator, you will see a key on your calculator, and I'm sure you've used this key before. It's this key right here. It's actually called the caret key, like a rabbit eats a carrot. Okay, that caret key, that's what we're going to use here. So what you're going to do on your calculator is you're going to type in 2. Okay, so type in 2, and then hit the caret key. And what it's going to do is it's going to pop a little box up here for you. Do y'all see that? And then you put in 20 up there. And then hit enter. And you're going to get a big number. You should get 1048576, which is actually 1,048,576 rectangles. Can you believe that? That's crazy, right? If I could fold this, if I could fold it 20 times, all right, so I folded it once, twice, 3 times, 4 times, 5, 6, 7. If I could do it 20 times, then I would have over a million rectangles, all right? Understand? Now, turns out, has anyone ever seen that show Mythbusters? It used to come on Discovery Channel. They did an experiment because there's a theory out there that you can only fold a piece of paper 13 times. Like that's the most you can ever get, like physically. Like you can't go past 13. So they got this real thin sheet of paper. They laid it out in an aircraft hangar. I mean, this thing was huge, like the size of a football field, this piece of paper. And they folded it. They even got a steamroller to help really flatten it out. And I think they got to 14. I need to go back and watch the episode, but I think they got to like 13 or 14. That's the most they could do. So the point is you could never do this. Like physically, you could never fold that paper 20 times. But theoretically, if you could, then you would have over a million rectangles. So look at this. This function that I just put here, if I were to ask you what the function is, what would it be? They all have as the base 2, right? So this is 2. And then up here is the input, right? So I'm going to call that my x. It's 2 raised to the x, right? This is not this function. This is a quadratic function. This is a parabola. This is a polynomial, right? This is that case right there, right? That right there, quadratic function, is that bottom example. That's not what's happening here. So this one, we already said, doesn't match up to this, right? We looked at that. But which one of these is growing faster? Do you think 2 to the x grows faster than x squared, or the other way around? What's one way you could check? Like if you plugged in 20 here, you got a million, right? What happens if you plug 20 into this one?
400.
You get 400. It's nothing, right? That's nothing compared to a million. This function grows very rapidly, right? Okay, so that's a first example, all right? This is an example of an exponential function right there, all right? The reason we call it exponential, why do you think we call it exponential? Anyone have an idea of why we call it exponential? So what is it about the exponent that's important in an exponential function? Like look at this one. The exponent here, right? For a polynomial, the exponent is a number, right? It doesn't change. But in an exponential function, the exponent is the variable. It's the thing that changes, and that's why we call them exponential functions, all right? So here's another example of an exponential function that I can show you physically. What was that? Did you hear that? Was that you, Paris? I heard it. I don't care. Okay, so look, let's do this one. I'm going to do a piece of paper again, all right? But this time, don't worry about the rectangles. I just have a piece of paper here. And let's say that the length of this is 1 foot. I know it's not, but let's just say this is 1 foot wide, okay? So I'm going to make a table here. I'm going to put cuts here. I'm going to put length here. All right, so if I don't cut this thing at all, how long is it? 1 foot, okay? So 0 cuts, 1 foot. Got it? Now I'm going to cut it right down the middle. I'm going to cut it in half with these really precise scissors that I have here, all right? So I've cut it in half. So I've cut it one time, right? How long is it? Half of a foot. Half of a foot. Okay? Now I'm going to cut it again in half. So what happens if I cut that in half? I throw this half away. How long is what remains? 1/4, because it's half of that half. So 2 cuts gives me 1/4. And then what happens if I do this again? 1/8, because I'm doing half of the half, right? So I keep on basically taking half of this, which means multiplying it by a half. So if you take 1/4, multiply it by a half, you multiply straight across, you get your 1/8. So 3 cuts gives me 1/8. And then what if I could do it 4 times? I should have 1/16. And the question then would be, what if I cut it, I don't know, 10 times? How long would it be? So again, you could keep doing it until you get down to 10, but the question is there a function that would give this to you? Right? So does anyone have a guess as to what this exponential function would be?
Would the exponent be negative?
It could be. You're a little ahead of the game with that. Let me ask you this. Can you rewrite all of these as something to different powers? So how about this? Is this 1/2 to the first power?
Yes.
Yes? Everyone agree that is? Is this 1/2 squared? Right? Is this 1/2 cubed? 1/2 times 1/2 times 1/2, that is 1/8, right? So all of these are just a power of 1/2. And then go back to the first one. Is this 1/2, what power would it need to be? 0. And it is, right? So our function for this particular example should be what? 1/2 in parentheses raised to the x power. Okay? This is an exponential function. This is a different exponential function. Just like we had, polynomial functions, they all looked different, right? They all, we could have all sorts of different examples of polynomials, different examples of rational functions. I sent you home to graph 3 of these, right? I've just given you 2 examples of exponential functions, all right? Let's do one more example. This one has to do with bacteria. Do y'all know what a petri dish is? A petri dish, right, is a little dish that they use in biology classes, and what they do is they have this dish that's completely sterile. There's nothing in it, there's nothing growing, there's nothing, right? And then what they'll do is, I don't know, they'll go wipe the handle of a door or something, and they'll put it in here and they'll close the dish, and then they'll come back a day or 2 later and they'll look and see what's growing, right? And they'll put it under a microscope and they'll say, oh my gosh, there's all sorts of bacteria on that handle, right? So this is a sterile dish that you try and see, what sorts of bacteria grow in it, all right? So let's say that there's this particular bacteria which triples itself every 24 hours. So basically every day. You have this particular bacteria that every day it will triple itself. It'll split, and 1 becomes 3. All right? And it does that every 24 hours. With me? How many bacteria will be present in 14 days? All right, so let's see if we can't first come up with a function that represents this growth. Right now, we don't know it's exponential, but obviously it is because I'm giving you an example of an exponential function. But let's convince ourselves that it is. So I'm going to make a table here. And here I'm going to put days. And here I'm going to put the number of bacteria. So let's say at the beginning, I place 1 bacteria into a petri dish, all right? And the clock starts. So at 0 days, that means when I start the experiment here, how many bacteria are there? I'm going to place 1 in there, right? So at 0 days, I have 1 bacteria. Okay, how many bacteria will be there after 1 day? The 1 is going to split into 3. So I can show you this visually. If you've never seen what bacteria look like, I'm going to draw it for you. So here's a bacteria. Okay, that's what they look like. And after 1 day, it's going to split into 3. All right, so 1, 2, 3. So now you've had 1 day, right? 1 day. And now you have 3 happy bacterias. All right. What's going to happen? So after 1 day, we have 3. How about after 2 days? How many will we have? We'll have 9. Because what's happening is each bacteria is now going to triple itself. So this bacteria goes into 3. This one goes into 3. This one goes into 3. And now you've got a total of 9, right? And then what's going to happen after the 3rd day? You're going to have 27. Each of those 9 become 3. So you're basically multiplying this 9 by 3, and you're getting 27. This is growing extremely fast, all right? It may not seem like that's fast, but wait till we answer the question, all right? So right now, we need to come up and figure out what's happening at 14 days, right? So what is happening at 14 days? Well, this looks exponential, doesn't it? If you can rewrite this as something to a power, like a number to x, then we're in business. So what number do you see here that we're going to use as our base? 3. So this is 3 to the first power. This is 3 squared. This is 3 cubed. And of course, if we go back up, this is 3 to the 0. So everything looks like it checks out good there, right? So it looks like our exponential function is 3 to the x. So we get on our calculator to answer this question, and we figure out what 3 raised to the 14th power is. And go ahead and do that. So if someone can give that to me. Just read out the digits. Or is it giving to you in scientific notation? Hmm.
4 million.
It's 4 million? 478 29 69. So you've got close to 5 million bacteria there within the first 14 days. All right? Some bacteria don't triple themselves. Some bacteria, they just split into 2. I just didn't want to use 2 again because then we would have had 2 to the x again. I just want to give you a different example. So, some bacteria, it takes them, a week to split. Some bacteria, they can do it in 2 hours or even less. It just depends on the bacteria. So for this example, this is what's going on. The most important thing is to understand its exponential growth. All right? Okay. All right. So in general, let me give you one more example. This one might be somewhat interesting to you. How many of you have heard of this thing, March Madness? Yes? What is March Madness?
College basketball.
It's college basketball. It's a tournament that the men's college basketball has. And what they do is they come up and they rank the top 64 teams in the country, and they put them into a tournament, and they make them play each other, and it's win or go home. Every single game is you win, you go, you lose, you're out, okay? And at the beginning of the tournament, they tell you who's going to play who, and they give you this thing called a bracket where you can go in there and you can pick who you think is going to win each game before the tournament starts. And you fill out the bracket and you try and figure out, who the champion's going to be. And you can go to like different websites and fill out these brackets, and then you submit your bracket, and then the tournament happens, and if your bracket is exactly right all the way to the champion, they're like give you like millions of dollars. I forget what the most recent prize is, but I think on ESPN it was, I don't know, I want to say several $1 million, all right? If you can fill out the bracket properly. No one's ever done it, all right? So let's see why no one's ever done it. So you have 64 teams, right? So let's just take a smaller example first. What if we only had 4 teams? I'm just going to call this Team A, Team B, Team C, and Team D, right? These two are going to play each other, and you'll have a winner. These two will play each other, and you'll have a winner, right? Yes? Okay, so starting out with 4 teams to start. You know what? Let's make it 6 teams. Can we do 6? E and F. What was that? Did I hear something else? It's okay. I'm wondering if I'm hearing things. So 6 teams start the tournament, all right? Okay, so if you were to just randomly, like if you knew nothing about basketball, and you just randomly picked who was going to win, then how many different ways could you pick this? Either A or B, right? So there's 2 possibilities of how this could happen, and there's 2 possibilities of how this could happen, and there's 2 possibilities of how this could happen, right? So if there's 2 possibilities here, and 2 possibilities here, and 2 possibilities here, then how many different ways could you fill out just that first game that happens? There's 8 different possibilities, right? Understand? Yes? Okay. Now, I really need 8 teams to do this right, but let's move on. Let's do the 64 teams, all right? So I have the first 2 teams are going to play, right? Whatever teams those are. How many ways can that happen? 2. And then the next 2 teams are going to play. How many ways can that happen? 2. Okay? And I'm going to keep doing this for all the games. Now, how many games am I going to have? Remember, there were 64 teams to start the tournament. Okay? So how many games will I have in that first round? 32 games, right? Because you can't have more than 32, right? So that means I'm going to have to pick this correctly 32 times, right? 32. So that's 2 I can do, right? It's 2 times 2 would be 4. And then the next one would be another one, 8, and then 16, and then 30. So that just picking the first round correctly, the different ways that could happen is 2 to the 32. That's how many different ways the first round can happen. But then you have to go, and those teams that won then have to go play the second round. So the winners of this now play each other. The winners down here play each other, right? And so there's 2 ways to pick this, 2 ways to pick this, and to keep going. How many games are in the second round? 16, because in the first round was 32. So this will contribute, and it's not adding to this, it's multiplying, times 2 to the 16. Okay? Then those teams go play each other. So these teams play each other and whatever. How many games will I have here?
8.
I have 8 games, so 2 to the 8. And then you go again, they play, right? So you get 2 to the 4th, that's 4 different ways. That's 4 games, right? That you have to pick right. And now you're down to the final 4. And that means there's 4 teams left. So how many ways can that happen? 2 to the 2. Because there's two games, there are 4 teams left, there's 2 games. You can pick each game 2 different ways. And then you get to the final championship game, which means there's only 1 game left. And there's 1 way to do that. Now, when we do this, when we multiply, if you have the same base, what you do is you add these numbers up. So someone on their calculator, we can do it in our head maybe. 32 plus 16 is 48, right? 56, 62, 63. So someone on their calculator, tell me what 2 to the 63 is. I might need to do this. Hold on. I'm going to do it. 2 raised to the 63rd power. All right, my calculator says 9.223372037 times 10 to the 18th power. This is good old scientific notation. What does times 10 to the 18 mean? You're going to move this decimal point 18 places to the right. So 9.223372037. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Put it right there. 0, 0, 0, 0, 0, 0, 0, 0, 0. That's how many ways you can fill out the brackets. That's how many different brackets can be filled. Does that make sense? So, where did my thing go? Oh, it fell in here. This number is huge, isn't it? Let me see if we can get our heads around this number. Okay. 1, 10, 100,000, 10,000, 100,000, million, 10 million, 100 million, billion, 10 billion, 100 billion, trillion, right? Tens of trillions, hundreds of trillions. What comes after trillion? Gazillion. No. Right? This is obviously a huge number. So how many people are on the planet? Anyone know how many people are on the planet right now? Let's go with 6 billion. That sounds like a good number. I'm going to take this number and I'm going to divide it by 6 billion. Right? Now 6 billion, what's 6 billion? So 1, 2, 3, 1, 2, 3, 1, 2, 3. So this is millions, so 6 billion. I'm going to divide it by that number. Okay? So divide that by 6 with 9 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9. And I get 1, 5, 3, 7, 2, 2, 8, 6, 7, 3. Why did I divide it by 6 billion? What do you think I'm getting at here? If every person on the planet, okay, filled out brackets, we would each need to fill out this many differently. So I would have to come up with what is this? This is about 1.5 billion. I would have to fill out 1.5 billion brackets, all of them different. And then you would have to do yours 1.5 million, all different than mine. And then the next person 1.5 million, all different from theirs. And everyone on the planet has to do that. And then we're guaranteed one winner. All right? That make sense? This is an astronomically large number. Now, the March Madness doesn't really work this way because, a lot of times, this is like Duke versus like UTSA or something, right? This team is always like, they just kind of got into the tournament and they're, you know what I'm saying? So the probability of Duke winning this game is pretty good, really good. And so this first game, maybe you can pick it. And I'll have to go look, but I think a few years ago, somebody got the furthest that anyone's ever gotten. They got the first round correct, and they got, I think, almost everything in the second round, with the exception of like a couple of games. I don't think anybody has ever got the first 2 rounds correct. Does that make sense?
Because some teams get upset.
That's right, because there's upsets, right? And so they call those bracket busters. Whenever someone has a team that wasn't supposed to win wins, it blows away a bunch of these brackets. But at the end of the day, I mean, getting the first bracket is pretty good. I mean, there's a lot of ways that can happen. Getting the second one, though, I mean, remember, this is 2 to the 63rd power. So even getting the first round right, you still have a lot of things you have to get right, right? So, okay. Why am I showing you that? Because that's math in the real world, okay? That's March Madness, brackets, that's exponential function right there, 2 to the x, that's basically it right there. It gets big fast. That's why when you watch the news or something, you'll always hear things like, you know, the crime on whatever side of town is growing exponentially. They love to throw that word around because it makes people think like it's growing fast. Yes?
Are you able to do an example of winning the lottery?
Yeah, lottery's different though. Lottery is a little different because lottery is a little more complicated because there's, let me give you a basic example. Let's just take like, you know those little padlocks where you have little dials on them that have the numbers on them, right? You put them on your little locker at the gym or something. So let's just say you have a padlock that has three dials. Well, let's say 4, okay? And this can be like any number 0 to 9. 0 to 9, 0 to 9, 0 to 9, right? So how many different ways can you set this first one? 10, actually, because 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, that'll be 10 digits. There's 10 different possibilities here, 10 here, 10 here, 10 here. And if you do that, that's 10 to the 4th, and that's going to be 10,000 different combinations that can be set, right? Which makes sense because you could have like 0, 0, 0, 0, right? You could have 0, 0, 0, 1, 0, 0, 0, 2, and you could count all the way up to 9,999. And that would give you the 10,000. Right? But lottery is different because with lottery, you're picking numbers, right? I don't play the lottery unless it gets real big. I don't play it, so you'll have to help me out here. You have to pick how many numbers?
There's 6. I think there's
6? Okay, let's just go with 6. Let's just say there's 6 in the lottery, right? So you pick this number. Now, this number can be any number between what and what? I don't know. I think it's
1 and 54.
1 and 54. Okay, so this could be 54 things, right? Right? Correct? This one, you can't pick the same number twice. So this can only be 53 things. This can only be 52 things, 51 things, 50 things, and 49 things. Does that make sense? So you would think that you just multiply these together, but that's not it, because the order doesn't matter. How you pick the numbers. So this number doesn't have to be, like, let's say that the winning lotto numbers are 3, 7, 14, 26, and how many we got here? Let's say 31 and 40. Let's say those are the winning lottery numbers, all right? You can have these in any order. Like when you pick your numbers, you could have your 3 here or your 3 could have been here. So the order doesn't matter, and so that changes the way we calculate. So it's not exponential, and it's not even as simple as that. It's not impossible, but in a statistics class you do that. It's called permutations and stuff. And then if you do the one that you have to get the Powerball or whatever, that one, right, where you have to pick that number correctly, that blows the odds way out. Because that number, these can be in any order. This one has to be the one that you called the Powerball. So that makes it, yeah. What they've done is they've started to make it harder to win because more people play when the jackpot goes up to like, you know, almost $1 billion, right? Like people are more inclined to play. All right, let's move on, sorry. Exponential functions. All right, so let's do a general definition. In general, an exponential function with base a is any function f of x that looks like this, a raised to the x. So I gave you 3 examples of exponential functions. What was the base of the first one? That was the rectangle problem. What was the base of that exponential function?
2.
2. And then the second example I gave you, I was tearing a piece of paper in half, right? What was the base of that exponential function? 1/2. And then what was the base of the exponential function with the bacteria? 3. Okay, so that number that's sitting down there is called the base of the exponential function, right? Now we do have some restrictions on this number. You can't put any number here. First of all, that a has to be positive, okay? You cannot put any negative numbers down as your base. If you do that, you're no longer looking at an exponential function, you're looking at something different, and we don't deal with that in here. And then we also have a condition that a cannot be 1. Because if a is 1, what is 1 raised to any power? Just 1. So that's not going to do anything. That function is just always going to stay 1. It's not going to look like it's growing or anything. All right? Everyone got that? That's the general look of an exponential function. Some number raised to a power. Now, the graphs of these are actually kind of interesting. We have 2 different possibilities when it comes to graphs. Do you remember with parabolas? We had the parabola either opens up or down. We had 2 possibilities. With exponential, we have 2 different things that could happen. All right? The first one is going to look like this. First of all, at 0, when we plug 0 into the exponential function, what does it spit out? What was it spitting out every time we plugged 0 in? What was coming out of it? 1, right? So we know that we're always going to have that point. That point will always be on the exponential function. Make sense? Mm-hmm. Because a to the 0 is going to be 1. And then to the right of this, it's going to grow, and it's going to grow rapidly, almost like a parabola. It'll start to grow. And on the left side, check out what it does. It starts to decay, and I'm putting a dotted line there. What do we call that? Back with rational functions, that dotted line, we called it a horizontal asymptote, right? So with an exponential function, on one side, it grows very rapidly, and on the other side, it actually gets closer and closer to 0, actually very rapidly, all right? So that's what an exponential function will look like. It looks like this, so long as a is bigger than 1. So that number right here, as long as it's bigger than 1, we have this, and this is called exponential growth. Okay, because when you read it from like a book from left to right, it grows, doesn't it? Now, the other picture you could have with an exponential function would be you still have this point, right? At 0 you get 1. But instead of having it do that, it's flipped over. So it grows as you go to the left, and it shrinks as you go to the right. This is what happens if the number is less than 1. And this is called decay. So when I was folding the paper and getting the rectangles, was that exponential growth or decay? Folding, when I was folding, what was our base? The base was 2, wasn't it? Right? When I was folding, not cutting, folding, right? When I was folding, the base was 2. 2 is bigger than 1. That's growth, all right? I was getting a lot more rectangles as I folded more, right? I got more rectangles. And then what about when I was tearing the paper? What was the base? 1/2, right? 1/2 is less than 1, but it was getting smaller and smaller, right? Now, we're not going to get into any real depth onto the graphs of these, all right? We're actually pushing forward to try and get ourselves to some problems that apply to the real world. But this is just a general picture of what they look like, all right? You have 2 different cases, growth or decay. Now, when it comes to the bases, we have 2 very special bases. Remember, A can be any number, right? As long as it's positive and it's not 1. So there are an infinite number of bases that we could ever have with exponential functions, right? You could have base 2, base 3, base 4, base 5. You could have base 2.6. You could have base anything, right? But there's two that are very special that we use all the time in physics, in chemistry, in the real world, in finance. And here they are. The first one is if A is 10. And that means your base is 10, right? So that would be this function right here. 10 to the x. Right, that's the first one. Now, why do you think that 10, having the base of 10 would be important to us? Have you all ever heard that our number system is base 10? Have you ever heard that before? Our number system is a base 10 number system. Y'all heard that or no? So when I write this number down, when I write that number down, everyone in this classroom agrees that that's 3,461, right? Yes? Yes?
Does it have something to do with the place value?
Yeah, it's the place values, exactly. That's what it is. So look, what this means is we have 1, 1, right? 6 tens, 4 hundreds, and 3 thousands, right? So this is really saying we have 3 1,000s plus 4 100s plus 6 tens plus 1 1, right? That's what that means? I mean, you would never write that number this way, but that's what it means, right? Yeah. Now I want you to notice this. This is the same as saying 3 times 10 cubed plus 4 times 10 squared plus 6 times 10 to the first power plus 1 times 10 to the 0 power. So this 1,000 is really 10 times 10 times 10, right? And this 100 is 10 squared. This 10 is 10 to the first power. And then this 1 next to it, there's a 1. And 1 is 10 to the 0. So this is really telling you how many 10 to the zeros you have, how many 10 to the 1s you have, how many 10 squareds you have, how many 10 cubes you have. And the next number, if there was one out here, right, like let's say I put a 7 here, will tell you how many 10 to the 4ths you have, right? So these digits represent the powers, how many of these powers of 10s you have. With me? So because our number system involves all these powers of 10, the base 10 exponential function is something that would be interesting to us, right? How many digits do we have in our number system? How many digits? Like when I wrote this number down, when I put that first one there, 1, how many possible things could I have put there? I could have put a 0 here, a 1 here, a 2 here, a 3 here, a 4 here, a 5, right? How many different digits do I have to choose from? 10, right? I have 10 digits to choose from here, 10 digits to choose from here, right? 10 digits, base 10, yes? Why do you think we use 10 digits and not 5 digits? I'm going way off, I'm sorry. This is just... Why use 10? Does anyone know how a computer works? What is a computer? Does anyone know the number system the computer works, or a computer uses?
Binary.
It's called binary. How many digits are in binary? 2. The only 2 digits there are 0 and 1. Okay? That's all there is in binary. So when you write a number in binary, it's like when you go to write the number, you can only put 0s and 1s. That's all you're allowed to ever choose from. So your first digit is something, how many of, like this first one was how many 10 to the zeros we have? How many, right, how many, this is 6, 10 to the first, 4, 10 squared. What do you think this is? Like if I write this number, this is saying how many what to what powers I have. How many digits are there? 2. So this is base 2. So this is how many 2 to the zeros I have. 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, 2 to the fifth. I know I'm going way off, I don't care. This says I have 1 2 to the 5th power, right? What is 2 to the 5th? What's 2 times 2 times 2 times 2? What's 5?
Because we wrote it down.
Yeah, we did it, right? 2 to the 5th? So that's really what? 32. Okay, so this is really a 32. Nothing here. How about 2 cubed? What's 2 cubed? 8. I have one of those. And then 2 squared is 4, right? I have one of those. And then I don't have any of these. And then 2 to the 0 is 1, so I have a 1 here. If I add these up, I get 45. So this number right here is the number 45. Okay? Why does a computer only use zeros and ones?
Because it was built that way.
Yeah, but why use zeros and ones? What is a computer? What is the only thing a computer knows?
Like on and off.
On and off. That's all a computer knows. You either have an electrical signal there or you do not. Yes, no, 0, 1. That's it. That's all it knows. So everything has to be translated from signal being there or not into zeros and ones, and then from that you're sending each other videos across the world. It's crazy that it's just a bunch of zeros and ones floating around everywhere, but that's what it is. All right. Every video you watch is a stream of zeros and ones floating through the air, coming into your computer, coming into your phone, and that zeros and ones are being translated into pixels on a screen. Crazy. All right, so why do we use base 10? Why didn't we just start with base 2? Why would humans use base 10 and not base 8?
Because it connects to
Computers want zeros and ones. Why? Because we have 10 fingers. We have 10 fingers, right? We count with these things, right? If we had 8 fingers, we would probably use base 8. It's the 10 fingers that are the basis for this being so important to us. Our numbers are counted, it's based off our fingers. Understand? The computer can't do this. A computer can only do signals, yes and no, so we have to use a different number system. So base 10 is important, all right? Now, the other special base, which is much more difficult for me to explain to you, is when the base here is this number. Now, have you ever seen that number before? Now, I know a lot of you have seen this number before. What's that number?
pi.
Pi, right? Pi, we use that with circles, don't we? So pi is approximately 3.14, right? And this thing keeps on going, right? And it never stops, and it never has a pattern to it. It's called a non-repeating, non-terminating decimal. It just keeps going. And I'll tell you a quick story. My cousin, right? His daughter is high-functioning, autistic high-functioning. You all know what that means? Okay, so the other day, it was her birthday party, and he was like, hey, check this out. My cousin was like, hey, check this out. She's 9 years old. He goes, I'm not her uncle, right? But she calls me Uncle Robert. So he's like, tell Uncle Robert what pi is. So I said, okay. I asked her, what's pi? And she recited pi, 3.1415, and she went out 100 digits out of her head. Crazy. 9 years old. I was like, whoa. So apparently at their school they had a competition to see who could memorize the most, digits or something. And she was second place. Crazy. Okay, so this is a number that keeps going. We're not going to get into the details, but it's an important number in mathematics. So important, in fact, instead of writing 3.14, we write the Greek letter pi. All right. Now, E is another letter that represents a very special number that's kind of like pi. It keeps on going forever, never terminates, never has a pattern to it. Okay, and E is approximately 2.718. Now, E is extremely important in mathematics. Extremely, extremely important. Can somebody in here tell me for both of these special bases, whether or not we have exponential growth or decay. And why? Are these examples of growth or decay? Growth. Why growth? Because a is greater than 1, right? If a is greater than 1, we have growth. So this, if I graphed it, would look like this. And this, if I graphed it, would also look like that. Now, they wouldn't be exactly the same. They would grow at a different rate, but they both are growth. This one right here, though, just grows a certain way. It just the way it grows is just perfect. We just, again, I can't, without doing too much, I'd have to go into calculus a little bit to explain it. All I can say is we were looking for a function. We as in humans were like, is there a function out there that behaves this exact way? We need it to do this, 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 this. We went looking for it, and this is the one, all right? And it's used all the time. We're going to use it here today, all right? So I want us to actually practice making a t-table for this one real quick, all right? So here's what I want you to do. I want you, on your calculator, I'm going to give you the x value. I want you to do e to the x, right? That's the function I'm working with here. Because I think everyone could handle 10, right? You just use that 10 and that caret key, and you'd be fine if I asked you, what's 10 squared, what's 10 cubed. But e to the x, there's a special key on your calculator for it. So first of all, what would happen if I do e to the 0?
1.
That should spit out 1. We know that, right? But what about if I plug in 1? So that's just going to give me e to the first power. But on your calculator, I want you to find your e key, and you'll see a key that looks like this. See that key? It's on the left side, third one down. And above it in green, you'll see e to the x. Do you all see that? So what you have to do is you have to hit that second key on your calculator first. That means you're going to use the green functions. And then hit that key. And your screen should be showing you this. If you're not using this calculator that we're supposed to have, then we're going to have to figure that out for you. Right, so what happens when you plug a 1 in there and hit enter? You get 2.718. And let's just go like 3 or 4 decimal places. All right, how about let's do 2. Plug 2 in here. So just do it again. 7.38 something. 389. Okay, here I'm going to ask you to do something a little different. I want you to plug in 6.2. No, you know what? 6.25. Yep, 518.012. So you need to be making sure that you can get this on your calculator, all right? And if you're not, let me know. Are you not, Elizabeth? You've got a look on your face.
That 7, because when I put it in,
You're using the one that we're supposed to have, right?
yeah.
Let me see. Oops.
Or maybe I put.
Oh, you put a 2 in front.
Oh.
See that 2? Get rid of that 2. No. It's just e raised to that power. Okay, now I'm going to ask you to try something a little different. Ready? I want you to put -4 in. Make sure you can get 0.018. Anyone have any issues? Let's do one more. I want you to plug in -2.653. Should get 0.070, something like that. Okay? All right. You hanging in there? All right, so we have 2 special bases. Now, we're not graphing these.